Okay, so page 3 again of the notes for section 3.5. We're just practicing graphing some rational functions here. So first, they're going to give us an outline here. First, find and graph all vertical asymptotes, or perhaps holes. Find and graph all horizontal or possibly oblique asymptotes. And then, if necessary, make an XY table and then plot at least 2 points on either side of the vertical asymptotes. And then we'll sketch the graph. All right, so let's start with this first one. Let's think about vertical asymptotes or horizontal asymptotes. Let me sharpen my pencil here. Gonna have to write kind of small to fit all this stuff in here because we're gonna make a table here too. All right, so vertical asymptote. All right, vertical asymptotes, that's gonna occur where? X equals -2, because that makes the bottom undefined. Horizontal, all right, I think this is case B where the degrees are the same. So this will be y equals 1. The ratio of the leading coefficients, right? 1 over 1, which is 1. All right, so now what we want to do, let's draw those asymptotes in. All right, so x equals -2, assuming this is the origin, x equals -2 would be here. And I would suggest that you draw these with a dashed line. Don't make them solid because you'll confuse the line you've drawn with the axes, and you don't want to do that. All right, so -2 and then up at 1. Okay, so now this will help us decide what x values we're going to put in our table. Our x values that we're going to use is the 2 integers immediately to the left. Don't pick values out here. Pick values immediately to the left of the vertical asymptote and immediate integers to the right. So the undefined one is at -2. So we'll do -4, -3. Let's do them from smallest to largest. So -4, -3, and then on the other side, we don't want to do -2, we want to do -1 and 0. Okay? So those are the x coordinates you want to use. Sometimes students have a hard time, thinking through those. Okay. And then we want to plug that into x minus 2 over x plus 2. So plugging a -4 in there, we get what? On top, we get -6. Divided by, on the bottom, we get -2. And so that should be a +3. I'm just say y. It's f of x or y. Okay, so that's 3. So let's plot that. So we have, and again, it's really easy to start from this point, but we're actually going from the origin here. So 1, 2, 3, -4, and we're going to do 3. 1, 2, 3, we're here. Okay, let's do -3. So plugging in -3 in here, we get what? -5, and then on the bottom, we get -1. And so that is -5. So at -3, 1, 2, 3, we're up at 1, 2, 3, 4, 5. And that's really all we're going to do. We're going to use those 2 points plus the asymptotes to help us graph it. Now, if you felt like you wanted to put in, like, I don't know, maybe -6 or something like that, you could do that, but you don't really need to. You want to sketch that and then just don't cross, don't touch, don't curve away from the asymptotes. So something like that. All right, and then put in 1. So you put a -1 in, you get -3 divided by -1 in there is 1, so that's -3. So we go over to -1, we're going to go down 3. 1, 2, 3. And then plug in a 0, so we get -2 over 2, which is -1. And so at 0, we're down at -1. Now you notice that there's a symmetry, but it's about this intersection point of the asymptotes. So from there, I went over 1, down 1, 2, 3, 4. I do the same thing. I go over 1, I go up 1, 2, 3, 4. So you can see there's a symmetry there. And then sketch that in. I didn't give you very big graphs here, but you can kind of see Again, make sure that you're getting close to, but not touching or crossing or curving away from the asymptotes. All right, and so the next one, vertical asymptote. The top does not factor, right? So we would try factoring perhaps to see if we can cancel anything, but it doesn't look like the top factors. And so vertical asymptote. Vertical asymptote is at x equals 2. So let's sketch that in. The graph is a little, the graph paper is a little tighter here. It's a little smaller, but it's there at 2. And then in this case, this is case C, the third case in the previous page, where the top degree is increase is 1 higher than the denominator. So we got to use synthetic division here. So as small as you can, because we're still going to need to make a table. Let's put a 2, and then in the box, and then next to that we're going to have 1, 0, 1, and put our remainder line there. So we bring down the 1, we multiply, that's 2, we add, that's 2, we multiply, that's 4, we add, that's 5. But we don't care about the remainder. All we care about is this. So that means that we have an oblique asymptote, and that is y equals x plus 2. Just coincidence that that's the same oblique asymptote we had before. So let's draw that in. So that's going to be a y-intercept of 2, and it's going to have a slope of 1. So it's going through all these corners. Okay. Now what we have to figure out is where this is. So we'll pick 2 points to the left, 2 points to the right of the vertical asymptote. So in our table, it's going to be a little tight here. I should have given you more room to do this. We're going to pick 2 values to the left. So we're going to do 0, 1. Can't use 2. We use 3, 4. The 2 integers immediately to the left and immediately to the right of the vertical asymptote is what we plug in there. All right, and so when we plug 0 in for that, we get negative 1/2. All right, so 0, negative 1/2, we're here. Okay, so we know we're going to be down in here and up in here, right? Opposite each other. We're not going to be in these 2 regions here, which sometimes we are, but in this case we're not. All right, so when we put a 1 in there, we get what? 2 over negative 1, so negative 2. And so that's 1 and negative 2 were here. Okay. So again, you could plug in more x values, but we know it's going to do something like this. And that's all we have to worry about. Right? So long as you clearly have 2 points, I'll be happy. But make sure that you have those 2 points clearly indicated. All right? So don't make the points really small and then draw your curve right over them and I can't see them. So make them sort of obnoxiously large, if you will. All right, and then when we put a 3 in, 3, that's 9 plus 1 is 10, and that's 1, so that is 10. So we're over here at 3. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're here. But you can count and you can see if I go over 1, I go down the same amount as I go over and up from the intersection of the asymptotes. Okay. And then when I put a 4 in, that's 17 over 2. So that'll be 17 halves. And so 17 halves, that's what? 8 and a half. So let's just count out 1, 2, 3, 4, 5, 6, 7, 8 and a half. Okay, just like this one was a half, this one's going to be a half as well. And so again, we're just going to sketch that in, and again, not touching, not crossing, not curving away from the asymptote. Okay, so that was an oblique asymptote. All right, let's look at the next one. The top doesn't factor, nor does the bottom. So I think we can just write down what our vertical asymptotes are and what our horizontal asymptote is. Vertical asymptote is what? X equals 3. Remember, too, not to put just 3 down. That won't get you any points for the equation of the asymptote. You have to put not just a 3. That doesn't tell me that you understand that it's vertical or horizontal. All right, and then the horizontal, that's going to be 2. Remember, the degrees are the same, so it's the ratio of the coefficients 2 over 1 or 2. All right, let's draw those in. X equals 3, that's here. And y equals 2, that's here. All right, and so we'll just make a table. Again, right now, think about what 4 x values you're plugging into the table. And so, so those should be the 2 immediately to the left. That's a 1 and a 2. We put them in order usually. Can't put a 3 in. We put a 4 and a 5. So 1, 2, 4, 5 are the best ones to do. Okay. All right. So when you put a 1 into this, you get 3 over negative 2. So let's see. I'll put a 1. And I'm going to do negative 3 halves, so I'm going to be down here. Okay. And then let's do a 2. So when you put a 2 in there, you end up with 5. 5 over negative 1. So negative 5. So 1, 2, start here. Over to 2, down 1, 2, 3, 4, 5. I think I should have given you a little bit bigger graph for this one. And again, if you wanted to put values over here, but 2 is all you really need, something like that. Okay, 2 is kind of like a bare minimum. Yeah, it probably would be nice to put, 0 in here, right? 0 would be what? Negative a third, so it would have been, it wasn't off by that much, but you just know as you get further off, you're going to get kind of stranger fractions that are going to be harder to graph. So just those 2 points, this one down here at negative 5 and at negative 3 halves. All right, now let's put a 4 in. So I put a 4 in, I get, on top I get a 9, on the bottom I think I get a 1, so that's 9, so I'm going to go 1, 2, 3, 4, up 9, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Should be just about 1 over, I think. Let's see if I counted that right. 1, 2, 3, 4, 5, 6, 7, 8, yeah, 9. So it should be right there. And then if I put a 5 in, 5, that'll be what? 11 on top and 2 on the bottom. So that's going to be 5.5. So over here we go 1, 2, 3, 4, 5.5. And so again, we're just going to kind of sketch that in, get close to the asymptote, but don't cross it, don't touch it, don't curve away from it. Okay. All right, and this last one, I think what we're going to want to do is try to factor this thing. Probably doesn't really, we don't really have room to factor it next to it, I don't think. So let me do it up above and below. So factoring it up above, what? 2x and x. Probably we want to do, well, 3. So it's got to be 3 and 1. I think I want the 3 with the 2. So we'll put the 3 there, the 1 here. So that's 6x. And then 1x, that difference is 5. So plus 3, that will give us positive 6x, minus 1. That'll give us a negative 1x. Okay, and then on the bottom, let's see what we would have gotten here. Again, 2x and x, it's got to be 1 and 1. They both have to be negative. All right, and so notice that this binomial will cancel with this binomial. So this function really reduces down to x plus 3 over x minus 1. Now, we're going to have a vertical and a horizontal asymptote, but we're also going to have a hole. Does that make sense? So we have a vertical asymptote. Where's our vertical asymptote? It's the badness that still exists in the denominator, right? So what x would make that denominator bad? So that would be x equals 1. All right, x equals 1. And then the horizontal asymptote, that's y equals 1 as well, because the degrees are the same, so it's the ratio of the leading coefficients. All right, and then also let's think about a hole. So where will the hole be? The hole is at 1/2, because that's the x value that would have made this part that canceled 0. And then we want to plug 1/2 into the reduced function. We can't plug it into the original one. It'll make it undefined. And when we plug 1/2 into this reduced function, you'll see, I think, that you get -7. So we have a vertical asymptote, a horizontal asymptote, and also a hole for this one. Okay, so let's put in those things. So we have an x of 1, so let's put our vertical here. And then we have a y also of 1, so let's put that in. And then we have a 1/2 and -7. So a 1/2, 1, 2, 3, 4, 5, 6, 7. So we have a hole right here. Okay, try to get that right on the line there, something like that. Okay. All right, let's make a table. So think about what x values. For some reason, I find students have a hard time figuring out the x values for these. So put down your 4 x values. All right, so again, we want to go to the immediate 2 to the left. So that's going to be -1 and 0, starting at the smallest and going up. So we have -1, we have 0, 1 doesn't work, we have 2 and 3. All right, and when you plug -1 into this thing, now we want to plug it into the reduced one, right? That will make it easier, and that's going to be -1. So we have at x equals -1, I'm down at -1. So I'm here. All right, again, careful, don't count. So it's easy to do. It's easy to start here and go over 1, down 1, and put it here. So get careful. With these tables, we're actually going back to the origin. All right, and then at 0, when you plug a 0 in, I think you'll see that you get -3. All right, so 0, -3, 1, 2, 3. And then, you know, this is also a point. Essentially, it's a hollow point, but you can sort of use that. So sketch this, something like that, and have it go through that hollow point. But, you know, don't draw a line through the point. We want it to be sort of hollow, all right, because it's a hole. All right, and then let's look at some points over on the other side then. 2, when I plug a 2 in, I get 5. So at 1, 2, go up 1, 2, 3, 4, 5. And then at 3, I get 3. So 1, 2, 3, 1, 2, 3. All right. And so let me try to sketch that in. Probably a little bit easier if I rotated it a little, but something like that. Again, you want to kind of get close to the asymptote. Don't stop when you're a unit away. You want to get within sort of a unit of the asymptote. That way, everyone kind of knows when they're looking at your graph that, oh, you understand what an asymptote does, right? So you don't want the asymptote here and have you curving and going like that, right? You want to sort of get closer to the asymptote so we can see that you understand what that asymptote is doing. The curve is getting closer and closer to it, never touching it though. But don't stop and kind of curve, like turn when you're far away from the asymptote. You want to kind of draw your curve until it gets closer. All right, let's look at this one example then. Example 6. So this is modeling in the real world. So vehicles arrive randomly at a parking lot entrance, but at an average of 2.6 vehicles per minute. The attendant can admit cars at a rate of 3.25 vehicles per minute, and that's like an average rate, right? However, since the arrivals are random, lines can, of course, form at various times. All right, so we're going to define an x. An x value in this case is what they call the traffic intensity. All right, traffic intensity x is defined as simply the ratio of the average arrival rate and the average admittance rate. So we have those for our parking lot, right? So the intensity for us is going to be 2.6 divided by 3.25. Let me find my calculator. All right, so 2.6 divided by 3.25, and that's simply equal to 0.8. So our intensity is going to be 0.8. Okay, now we have this function. It's a rational function. It's defined as, the function is defined as the average number of cars waiting in line to be admitted into this parking lot. All right, and it uses an x value, right? It uses an x value. So this is the x value for this particular lot that they're talking about, but this is for essentially any parking lot. All right, it's kind of what they're looking at. Okay, now the traffic intensity x, the value that we're going to plug into this. Now this, we have a particular value, but they're doing it for all possible values. So maybe a different attendant is working one day and the admittant rate is slower or faster, depending on how efficient that attendant is. So this isn't always going to be the traffic intensity for all parking lots, or even this parking lot all the time, but this is their average. Okay, so what we want to look at is the domain is always x between 0 and 1. All right, so you can't have something less than 0 here because it's the arrival rate divided by the admittant rate. If it's 0, no one's coming into the parking lot, right? And you can't have on average, if it makes sense if you think about it, your x can't be bigger than 1 because then the line getting in would just get bigger and bigger and bigger, right? If you on average are trying to admit more people than you can let in, then your line is just going to keep getting longer and longer and longer. And we'll see that, I think, when we graph. Okay, so we want to graph this thing, so let's make a table to graph some values. Okay, and let's think about asymptotes. What vertical asymptote are we going to have? And so that's going to be at x equals 1, right? So I kind of made a weird graph because I knew what this sketch was going to look like. So here we have a vertical asymptote. Okay. And so let's just pick some values. So let's just pick the 4 values, 1, 2, 3, 4, along here maybe. All right. Or let's do like 0, well, we know what that's going to be. If I put a 0 in here, it's going to be 0, right? If, the x in, if the intensity is 0, that means the top has got to be 0. And so that means no cars are coming in. That's the number of cars waiting is going to be 0, right? So that's simple enough. All right, so let's try 1/4. So when we plug a 1/4 into this thing, we get what? 1/16 divided by 1/4. So 1 minus 1/4, that's 3/4 times 2 is 3/2. All right, so we have 1/16 over 3 halves. If we want to think of that as a keep, change, flip, 1 over 16 times 2 over 3. So that's, I think, what, 1 over 24. So pretty small. Let's just like put it really in there, really, really close to 0. All right, let's try 1/2. All right, so 1/2 squared, that's 1/4. And then we have over 1 minus 1/2 is 1/2 times 2, that's 1. So that's going to just be equal to 1/4. So that's a little easier to plot. 3/4. 3/4, so that's going to be 9/16 divided by, let's see, 3/4. 1 minus 3/4 is 1/4, times 2 is 1/2. And so that's going to be the same as 9/16 times 2, or 9/8. So here we're at 9/8. That means we're at 1 1/8. All right. And so I think, let's see, if we tried putting another value, I think we would get something close to 3. So if we sketch this, just kind of see what's going on here, you can see, right, we get something like this. All right, so it says compute the average number of vehicles waiting in line to enter this parking lot, right? So it's like the X value for this parking lot is 0.8. So simply find what F of 0.8 is essentially what they're asking us to do there. Okay, so that's going to be 0.8 squared over, let's see, it's going to be 2 times 1 minus 0.8. So that's going to be 0.64 over, let's see, we're going to have, this will be 0.2 times 2 is 0.4. And so I think if you reduce that, that will be 1.6. All right. So, and if we look, I guess that would probably be this value. If we did 0.8, let's see, that's 1. 0.8 would be something here. And so 1.6, that would be about here, I guess, right? So we can kind of see that agrees with our curve more or less. And then, so that's the answer for that one. And then D is, what would happen to the number of cars waiting to enter if the traffic intensity approached 1? So as the traffic intensity gets closer and closer to 1, you can see clearly as X approaches 1, F of X would approach positive infinity. Okay. All right. The homework then is listed here. Remember times 5 is the multiples of 5. This homework is due next class.